Hello and welcome. Today, we're diving deep into a war that's fought on a microscopic scale, the battle our own bodies wage against cancer. We're going to explore how one of medicine's most powerful weapons, chemotherapy, actually works by first understanding the enemy it was designed to fight.
So, let's start with a pretty simple question, but one that has huge consequences. What if a single cell in your body just forgot how to stop copying itself? This isn't just a thought experiment, it's literally the origin story of cancer.
Because that's exactly what cancer is. It's not some invader from the outside like a virus or bacteria. It's our own cells gone rogue. They get this relentless, single-minded focus on growing without any control, blowing past all the body's stop signs and starting to invade the tissues around them.
To really get a handle on this, let's think about it with a simple analogy. Imagine cancer isn't so much a disease, but more like a broken machine. Specifically, a copy machine that's gone completely haywire.
Think about it. A healthy cell is like a really well-behaved office copier. It only makes a new copy when it gets the command, and it stops when it's told. But a cancer cell, that's like a copier where the print button is just jammed down, and it's churning out endless, often faulty copies that start piling up, messing up the whole system, and ignoring every single cancel command you throw at it.
So, the big question is, how does a cell go from being a normal, functioning part of the team to a total renegade? Well, it acquires what scientists call the hallmarks of cancer. But for us, let's just call them what they feel like, really dangerous superpowers.
Superpower number one, they learn to create their own go signal. Normal cells are polite. They wait for instructions from the body before they divide. Cancer cells, they basically hotwire the system. They write their own permission slip to grow, telling themselves to divide constantly. Now, of course, our bodies have safety features built right in. There are special genes that act like the brakes on a car, telling a cell to stop dividing if something's not right. So what's cancer's second superpower? It learns to cut the brake lines. It just flat out ignores those critical stop signals.
And then we get to what is maybe its most chilling superpower, resisting its own death. See, healthy cells that get damaged are actually programmed to self-destruct. It's a process called apoptosis, and it's a vital safety measure. Cancer cells figure out how to find the off switch for this program. They become, for all intents and purposes, immortal, and just keep multiplying no matter how damaged they get.
So now, armed with these incredible superpowers, the cancer cell starts its relentless campaign of division. And the arena where all this action takes place, the actual process of a cell copying itself, is called the cell cycle. This is our battlefield.
Every single cell that divides in your body follows this predictable four-phase process. First it grows, then it copies all of its DNA, then it gets ready to split, and finally, it divides into two. It's like a biological assembly line. But here's the crucial part. This predictable, orderly process is also cancer's greatest weakness. It's the very thing that medicine has learned how to attack.
And that brings us to the arsenal. See, chemotherapy isn't just one drug. It's a whole class of drugs, but they all share a common strategy. They are designed to interrupt that cell cycle we just talked about, and they specifically go after cells that are dividing really fast.
Generally speaking, chemo drugs use two main strategies. Some are like snipers. They're designed to attack cells only when they're in a very specific phase of that cycle, like, say, when they're actively copying their DNA. Others are more like bombs. They can damage or kill a cancer cell at any point in its life cycle, no matter what it's doing.
Let's take a closer look at one of those bomb types, the alkylating agents. Their method is brutally effective. What they do is they damage the cancer cell's DNA directly. They create these chemical links that basically glue the two strands of the DNA helix together. And if that DNA can't unzip to be copied, the cell can't divide. Game over.
A classic example of this is a drug called Cyclophosphamide. It's used to treat a lot of different cancers, things like lymphomas and breast cancer. But its effectiveness comes with a price, and you can see that price right in its most common side effects: hair loss, nausea, and damage to our bone marrow. Which brings us to a really important question.
If these drugs are so good at killing cancer, why do they have such a devastating effect on the rest of the body? I mean, why the infamous side effects that everyone knows about?
And the answer to that really gets to the heart of chemotherapy's challenge. Its greatest strength is also its greatest weakness. It's designed to attack rapidly dividing cells, but here's the thing, it can't tell the difference between a cancer cell and a healthy cell that just happens to divide quickly. And we have lots of those. Think about your hair follicles, always growing, or the lining of your stomach and intestines, which replaces itself every few days, and your bone marrow, constantly churning out new blood cells. Chemo hits them all. It's the collateral damage in this internal war.
But the story doesn't stop with collateral damage. The big takeaway here is that while some of these weapons are blunt instruments, the war itself is getting smarter, more strategic, and way more targeted.
For instance, let's look at one of those sniper drugs, a class called antimetabolites. Their strategy is much more subtle. It's really clever. They're designed to look almost exactly like the natural building blocks of DNA. So, a cancer cell, in its crazy rush to copy itself, mistakes these decoys for the real thing and pulls them inside. But once they're in, they jam the replication machinery from the inside out, stopping the cell dead in its tracks. It's a much, much more precise attack.
And really, that's where the battlefield is today. We've gone from powerful bombs to precise snipers, and the strategy against cancer is getting refined all the time. It leaves us with the final and pretty hopeful question. As we continue to decode every single page in cancer's playbook, just how precise can our weapons become?